Welcome back. We have spent the last several videos discussing sampling distributions for sample proportions. And so for a quick review before we pivot to a different type of sampling distribution, let's review what we've learned here, since a lot of this will come in handy for what's about to come next. So given a population, it could be any population, take all possible samples of size n. So from that large population, take all the samples you possibly can from that population of a given size and calculate p hat, the sample proportion of success for each of those n samples, or for each of those samples of size n. Okay, so you've got a bunch of p hats now, each one representing the proportion of success for your random variable in a given sample. We're just describing what a sampling distribution is here. All of these p hats that you've got, if you arrange them in a histogram, they would create a sampling distribution of a sample proportion for samples of that size. And one of the hallmarks about sampling distributions to remember is the sample size defines the sampling distribution. So given the same population, if you take samples of size 20 and then samples of size 60 from that same population, those two sampling distributions will be distinct. They will have different parameters. So the sample size that you take is important. And for a sampling distribution, all the samples have to be the same size. So once you have that theoretical sampling distribution of all the possible sample proportions, if all the individuals in your population are independent with respect to whatever your random variable is, and the sample size is large enough, which we checked with these conditions here, n times p has to be at least 10, n times 1 minus p has to be at least 10. If those conditions are met, then the sampling distribution of that sampling proportion, of that sample proportion, can be approximated with a normal model, with a mean of p, the population proportion, and a standard deviation of square root of p times 1 minus p over n. So we're saying no matter what the population is, no matter what the random variable, as long as the individuals are independent, and as long as your sample size that you're taking is big enough, the sampling distribution of those p hats is going to be approximately normal in shape with these parameters. We also note, because of this, the sample proportion p hat is an unbiased estimator of the population proportion, because the mean of the distribution is p, the population proportion. So this represents the mean of the sampling distribution. Writing it this way also means that. It's the mean of the sampling distribution for sample proportions is p. So it's an unbiased estimator. P hat is estimating what it's trying to estimate. And if you've got two sampling distributions, p hat 1 and p hat 2, if you meet all the conditions, if your groups, if your population individuals are independent, and if you've got these conditions met for both populations, then you can take the difference between those sampling distributions, and the sampling distribution of that difference also has a normal model. Well, it's approximately normal, so we use the normal model, with a mean of p1 minus p2, and with this standard deviation. I hope summarizing all that hopefully makes a little more sense of what it was we were talking about, because we're going to put the idea of using this for sample proportions off to the side. And we're going to see how things are the same and how things change if instead we look for sampling distributions of sample means. So in the past, we said that the sampling distribution for the sample proportion of students who passed the AP Stats exam in a recent year, the sampling distribution had an approximately normal model, it met the conditions, with a mean of 0.609 and a standard deviation of 0.069. So we could interpret that as, if we took all samples of, I think it was size 50 students who took the AP Stats exam that year, and we took the sample proportion from each of those samples of size 50 and looked at that distribution, it had an approximately normal shape, and the mean value for those sample proportions was about 60.9% of students passed that exam with that standard deviation. Now, I don't want to focus on whether someone passed or not. I want to look at the scores themselves. Because passing or not passing is important, but the actual score is also important. You can score anywhere from a 1 to a 5. 3 or higher, I think on every single AP test, 3 or higher means you pass. A 1 or a 2, and you don't pass. Let's look at the scores themselves. So we're going to let our random variable x now stand for the actual score that a student got on that AP Stats exam. This is information available from the College Board. So over 200,000 students took the AP Stats exam that year. The mean score was 2.88, and the standard deviation was 1.37, and that's for the entire population. Okay, so even though over 60% of students passed, the average score was only 2.88. And I believe, if I remember correctly, the reason for that is a lot of students who didn't pass got 1s. And a lot of students who passed got 3s and some 4s. I think 5 was the least common score. So the average score was actually below a 3 of passing, but over 3/5 of students passed the test. So let's suppose that we took all possible samples of size 50 students and we took a look at their scores instead of just whether they passed or not. Could we come up with a sampling distribution for the mean score of each of those samples? Not for the proportion of students who passed, but for each sample of size 50, we could calculate the mean score among those 50 scores, and we could do that for every sample of size 50 from the population. Could we create a sampling distribution for sample means? Yes. Let's talk about how that would work. So to repeat, we're taking all possible samples of 50 students who took this test. We're taking their scores, so we've got 50 scores per sample, and we're calculating x bar, the sample mean, for each of those samples of size 50. So we're going to have an x bar for this sample of 50, an x bar for this sample of 50, an x bar for this sample of 50, so on and so forth. We're going to have like thousands of these x bars, right? Because we're only taking samples of size 50 and there are over 200,000 students who took the test. So we're going to have lots of x bars here. We can create a histogram of those x bars. And yes, in fact, we can create from those x bars a sampling distribution for the sample mean. Now, not for sample proportions, because we're interested in the sample mean scores. Okay, so sampling distribution for sample mean is going to be a little different than when we talked about taking the sampling distribution for sample proportion. So let's first start out by saying what the mean and standard deviation, the parameters for this sampling distribution, are going to be. We'll talk about what shape or what model we can use after that. So the mean first. And again, let's see if we can come up with this on our own. This will be more fruitful than if I just give you the formula. So we know that the mean score for every student in the population is 2.88. So what we did was we took samples of size 50, all of the ones that we can, and we're calculating the mean from each of those samples. If we were to create a histogram of those sample means, what value would you expect to be smack dab in the middle of that sampling distribution? If you're guessing any number other than 2.88, I'd like to know why. Right? If we're taking sample means, then the mean of those sample means should be the population mean. And in fact, it is. The mean of the sampling distribution of sample means is the population mean. And I mean it. So again, the mean of the sampling distribution of sample means is the same thing as the mean of the original random variable, right? Some places you'll just see this denoted as mu. It won't specify that it's the mean of the random variable x. So if I had just called this the mean, as long as we knew that the random variable we were talking about was this one, I don't want you to get caught up in the notation. Mu x is the same as mu, right? It's the population mean. So let's talk about the standard deviation next. I admit I'm going to be a little lazy here. I'm just going to give you the formula for the standard deviation of the sampling distribution. The standard deviation of the x bars is the standard deviation of the original variable, the standard deviation of the individuals, divided by, oh, geez. Oopsies, this is an n. It's the standard deviation of the original random variable divided by the square root of n. Now, let's think about this. What this means is the standard deviation of the sampling distribution is always going to be smaller than the original standard deviation of the population. Why? In fact, it's not just going to be smaller. It depends on n. The bigger the sample size you take, the smaller this quantity becomes. The bigger your sample size, the smaller the standard deviation of the sampling distribution. Why is that? Let's think about it. All right? This standard deviation is of individual scores, right? Scores of individual students. So you've got students getting 1s, 2s, 3s, 4s, and 5s. And I'll tell you right now, a lot of these students got 1s. Okay, so this standard deviation is calculated by taking every individual student's deviation from the mean, squaring it, dividing it by n minus 1, and then taking the square root. Okay? So the calculation of this standard deviation involves 1s, 2s, 3s, 4s, and 5s. The standard deviation of the sampling distribution is only determining how far away from this mean the x bars are. And I'm going to tell you right now, there aren't going to be a whole lot of samples of size 50 that have all 50 scores being 1s. So the vast majority of these x bars are going to be closer on average to this score than the individual scores were. You're going to have lots of x bars that are like 2.9, 3.1, 3.2, 2.6. Those x bars are going to tend to be much closer to the mean than the individual scores were. So that's just one way of seeing why this formula makes sense. Why did I go through the effort of trying to explain that in context? Because the number one mistake students make with sampling distributions of sample means is that they assume that the standard deviation of the sampling distribution is the same thing as the standard deviation of the original random variable. But I want you to know, if you know you're dealing with a sampling distribution, if you're dealing with the variability of sample means, you gotta divide by that square root of n. Because this standard deviation is much smaller. You'll find that this sampling distribution is much tighter to the mean than the original population random variable. Okay. So, if you want to know how this was derived, page 456 in your textbook has a nice little math box that shows you that derivation. If you're a math nerd, Mr. Z would love to see that, I'm sure. And maybe you do too. So that is how you determine the population parameters for the sampling distribution of the sample mean. So if we wanted to calculate that sampling distribution's standard deviation, we would plug in the population standard deviation in the numerator, 1.37, and divide by the square root of our sample size. We said we were taking samples of 50 students, so we divide by the square root of 50 and we get 0.194. So again, the sampling distribution standard deviation is going to be much smaller than the population standard deviation, because you're taking how much does the typical x bar vary from the mean rather than the typical x value. Those x bars are going to be more tightly packed together. So, a question for you. You finally get to do some calculations on your own in this video. How would these parameters, these two, change if we took samples of size n equals 200? Same population, same random variable, but instead of taking samples of size 50, we take samples of size 200. I want you to calculate those new parameters and compare and contrast how they change for a sample size of 200 compared to a sample size of 50. Go ahead, take a second, pause the video, write that up, and then come back when you're ready to compare your results. I hope you came up with something like this. The mean of the sampling distribution does not change. It's just the mean of the population, which is just 2.88. No matter what your sample size, the mean of the sampling distribution will be the same. And that worked the same way with the sampling distribution for sample proportions. The mean of that sampling distribution was always p, no matter what n was. Okay, so the mean of the sampling distribution will always be equal to the mean of the population. And by the way, that means that the mean, the sample mean, is an unbiased estimator of the population mean, since the mean of the sampling distribution is the mean of the population. Now, for the standard deviation of the sampling distribution here, we use the same formula, population standard deviation over the square root of n. Population standard deviation still 1.37, but our n now, our sample size, is 200. So our denominator is bigger, which makes the standard deviation smaller. The bigger the sample size you take, the smaller the standard deviation is going to become. Okay, so you can write something like that. If this were on a free response question or something, you would make these calculations showing your work, and your explanation should look like that, but it should probably include some context of some kind. So you might say the mean of the sampling distribution of sample means of AP statistics scores would stay the same for both sample sizes, but the standard deviation of the sampling distribution decreases with a larger sample size. Okay, just including some context in there would turn that response from possibly a P to an E, which is what you want. Similar to when we discussed the standard deviation of the sampling distribution for sample proportions, the formula for the standard deviation of this sampling distribution requires meeting a condition of independent individuals. If the individuals within the population are not independent, then this formula is not accurate. So, the condition you need to meet is one of either sampling with replacement, which in practice we're never really going to do, although I suppose it could happen in certain populations, or our good friend, the 10% condition. As long as we're sampling less than 10% of the population, then we can assume that the probability of something or the sample mean doesn't change much from each individual you take out of the population. So we can assume that individuals are close enough to independent that this formula is appropriate. So we are now aware that we can take the sampling distribution not just for sample proportion, but for a sample mean. And we know what the parameters are and how to calculate them and how to interpret them. They have a similar interpretation as the ones for sample proportions. This would mean that the average sample mean for 50 AP Stat student scores is 2.88. And sample means vary from this mean of 2.88 by an average of 0.194. Okay? Now, what model do we use? What model can we use for this sampling distribution of the sample mean? We have a problem here because for sample proportions, we could always use the binomial model. As long as we have Bernoulli trials, which we do if we meet those conditions, for sample proportion, we can use the binomial model. We also learned that we could approximate it with a normal model as long as the sample size was large enough. What model can we use for the sampling distribution of a sample mean? Man, it would be absolutely wonderful if we could use the normal model, because that's literally the only one that you know about that could possibly work. It'd be great if we could model the sampling distribution using a normal model. And luckily, we can. The central limit theorem is here to save the day. The normal model was our only option, and because of the central limit theorem, we can use a normal model for the sampling distribution of a sample mean. So, the central limit theorem is our best friend. It really is. And this is what it says. The central limit theorem, or CLT, states that when the sample size is sufficiently large, a sampling distribution of a sample mean will be approximately normally distributed. It's amazing. For any population, the sampling distribution of the sample mean will be approximately normally distributed as long as the sample size is sufficiently large. Notice, we don't have to have a population that's approximately normal or even symmetric. We could have a population of any shape. It doesn't matter. If we take all the different sample means for samples of a given size from a population and look at the distribution of those sample means, as long as the sample size we took is large enough, and we'll talk about that in the next video, that distribution of X bars will be approximately normal. And that's incredible. This is one of the foundational theorems, results in all of statistics. In all of my years in school studying statistics, this may well be the single biggest deal. So it's kind of amazing and sad that you learn it so early in your statistical careers. We're going to talk in the next video more about how we can use this result to say things about the sampling distribution of a sample mean, but I'll leave that to the next video because this one's been going on long enough. So, we will continue talking about this in the next video. The next video I anticipate will be the last one over chapter 17 in the textbook. So this is a chapter we started all the way at the beginning of the unit. The homework for chapter 17 won't be due quite yet. Check Canvas for when that is, but you should probably start working on that homework before the day before it's due. So if you've got some extra time, look at the first few problems in the chapter 17 homework. You should be able to work through those. The only problems you won't be able to answer at this point are ones that involve sampling distributions for sample means. Anything that has to do with the central limit theorem or sample proportions, you should be able to tackle. After the next video, the progress check for the free response questions for Unit 5 will also be complete. You should be able to answer those free response questions. That due date will be coming soon, so make sure you check Canvas for that again. And there is a progress check for multiple choice in Unit 5, Part C, that is also coming up. So you've got those three things: Chapter 17 homework, progress check for free response, progress check for multiple choice. Those are all going to be coming due in the next few days. So check Canvas for those, make sure you get those done in preparation for your unit test. I anticipate there will be 2 more videos after this in Unit 5. Then you'll take your unit test, and then we'll do some review from what we've learned this semester in that last week before winter break. So that's it for now. We've introduced sampling distributions of sample means. You now know the parameters, how it's constructed, and the fact that under the right conditions, you can use the normal model for it. We'll talk more about that in the next video. We'll see you there. Take care.